This talk is about LabVIEW for composing and simulating quantum circuits. First, I will talk about the importance of this topic and the motivation behind it. Then I will show the project that I am working on that. As you may know for now that this year's Nobel Prize in Physics is given to scientists who work on the quantum information science. And this shows that how important this topic is. And for the quantum circuit, if you look at the Wikipedia definition, and the quantum information theory, a quantum circuit is a model for quantum computation similar to classical circuits, in which computation is sequence of quantum gates, which I'll talk about them, and measurement initialization of qubits to known values and possibly other actions. On qubits and these quantum gates are two new concepts I will show you in shortly. And to do that, there is a website called quantumcircuit.com, and here we can draw and write our code, our quantum circuit code, and simulate and run an actual quantum computer. So here, for example, we make two entangled qubits. We have a 1 qubit, and I apply a Hadamard gate on that, and then I apply a X gate, and I put a X gate on the second qubit and make a control NOT gate. So the first qubit is a control, and the second qubit is the target qubit. This way, we can have a 2 qubit entangled. This is called the Bell state, and if we see, we also have this equivalent code, and if we simulate it, we can see that these two states are entangled. This is a quick introduction to what I'm going to talk about. So we can see that there is a probability, 50% to both qubits to be 0, 0, and 50% to both qubits to be in 1, 1. So they are entangled. If we know one of them, we can be sure about the other qubit state. And another very famous composer is from IBM. And here again, we have the similar approach. We have gates, and we have a code here and the circuit here. These are quantum wires. Again, let's make the similar and circuit and see the result that is similar to the previous one. So what I'm saying here, that these interfaces are at the front end. They are not actual coding. The actual coding happens here. But it is very useful for people, researchers in with different background, to see the circuit itself. Engineers, electronics guy, and the other physicists, they need to see the actual circuit to have an idea about what's going on. There are actually lots of simulators written in different languages. This is a website that shows all the languages that are involved. The list goes on: C, C++, and Julia, and MATLAB, and Maxima, and Python, also Scala. Almost any major programming language has its own simulator, except LabVIEW. But LabVIEW has a huge potential and huge advantages in my idea to other languages. This is what a toolkit that I developed and put it on VIPM. And in this presentation, I will talk about that. But before that, I will talk about my favorite hero, Masih Halinejad, as a living giant among us. She is Iranian journalist, author, and women rights activist. And she's founder of the several campaigns against compulsory hijab. And I saw the most proper one to show as a giant, female giant living with us. And you can follow her. She won lots of awards, and I'm sure that we will hear from her much more. And if you want to follow Iran movement and see the history maker in action, follow her. So let's go to the the toolkit that I developed, and that there's a template for QuVI, which I called this toolkit. It stands for quantum VI. And if we open this template, we see a for loop, which is already populated with some circuits nodes and 2 qubits. There's an initialization node, and there is a for loop, and there's a start point for each loops and a release loop. This is a little unconventional arrangement, but it works for quantum circuits because we have to deal with parallel circuits and parallel computation. And there's a for loop because at the first loop we need to compose our circuit, and at the second loop I put the simulation. So this is the way I came up. And if we go to the palette, there's a palette for the QuVI and gates, similar to what we see in other programming. But here we are actually programming it is not a front end, or this is the actual coding happens. And this shows how advantages could be, LabVIEW could be. So I connect this and make a similar circuit to the previous one and connect them. And as you can see, this is the polymorphic, so it changes to appearance to similar what was in other programs. And this is our very simple Bell state, two entangled photon, two entangled qubits circuit. To see the result, we can connect the probability node, and after running, surely we can see again the similar result: 0, 0, 50% for to be 0, 0, and 50% to be in 1, 1. So I close it and go immediately to the project Explorer. Here there are some examples which I will talk about to show the importance, to show the benefits, advantages LabVIEW over other languages. But before that, I want to open the initialized circuits here. We can see how the circuit cluster shapes and what kind of method I used for as a global variable Q with size 1, because we are dealing with parallel and computation. We're gonna need propagate the data between the different part of element of the circuits. We have Qs with size 1, ones for size composition. I'm not going to the details, but another important thing is that also I included the abstract class for mathematical engine of the program, and this is abstract class should be populated, override with some concrete class. Right now I only have one class, and it's a very simple and basic, but slow one, let's say. But it shows the concept. So later we may have a better engine, mathematical engine, because these circuits mostly use linear algebra. Maybe we have a GPU accelerated linear algebra, and we can replace easily. So other elements and 2 loops for loop. I close it and I go to the teleportation example. The LabVIEW, coding with LabVIEW really helps us to teach and understand this protocol in its most intuitive way, in my idea. So we have Alice and Bob. Alice wanna send her message to Bob, and there is a protocol for that, and which is shown here, in its best way. We have comments. We can do some classical logic on our circuit. So Alice has two qubits, and she makes one of her qubit with Bob's qubit entangled, like similar to what we did already. And according to the protocol, she applies CNOT to her entangled using her message as a control, and then applies the Hadamard to her message, and then measures both of them and sends classical bits to Bob. Bob and Alice can be separated as much as they want. They can be at the two ends of the world. But as soon as Bob receives the classical bits and applies these gates according to if it is 1, if it is 0, according to the protocol, the state from here teleports to Bob immediately. That spooky action at distance is this. So if I run this, you can see every time I run several times, every time the classical bit that we changes, but the message sent and receive match is the same. So this, apart from educational part, it is also we can use this for serious coding. Another example is a Grover search, which shows the high more benefits of the how advantageous can be this approach. In the Grover search algorithm, the idea is that for searching, it can be happen much faster. A quadratic speed up comparing to classical search. Here we have 4 qubits and the total state of 2 to the 16 different states. In classical, in average, we need 16 over 2 or 8 search in our black box. This part can be considered as a black box. We don't know. We want to search and see which state we have. But in quantum Grover search example, using quantum amplification, we can reduce the number of search to 3. So 8 to 3. If we increase the number of the states, it will be, the difference will be considerable. Here again, we have this one, this loop, which should be repeated 3 times. And this shows how LabVIEW, coding LabVIEW really benefits. You can make a loop, which is not possible in other, GUI-based programming, and run this 3 times. So if I run this, yes, for sure, you will see that it says that more than 95%, there is a probability that we can find our state in this particular one. And if I want to compare it, and before going to the other program, I want to show the structure of project. We have polymorphs and classes and abstract classes, which I talked about. And if I want to compare it with the approach using IBM Composer, Quantum Composer, it will be this long circuit, which takes more space and hard to read. And as you can see, the IBM Composer start to put some classical statements like if, and because we need to have classical and quantum logic at the same circuit, sometimes we need to do some classical and then do some quantum computation. So it is very beneficial to have quantum and classical logic at the same code, like in our case. And for the future, I have only 1 minute. For the future improvement, it can be accelerated. Recently, NVIDIA published SDK for quantum simulations, quantum circuit simulation. It shows that how much attention is this area. So later improvement could be implementing this SDK in our code, and also there is a room for other improvements. This example shows how a circuit can be optimized, and the optimization can this uses a graph theory to optimize this complicated to this simple one. So maybe we can use scripting to modify the code itself, some kind of meta coding, meta programming. And I know this is very, tricky, part, but I wish I can do, and I hope to finish that. Thank you for your attention.